In the previous video, we gave a pretty cute application of the concept of degree of map of sphere to studying fixed point free action on the even sphere. Remember we said that the only group that acts freely on the even sphere is Z mod 2Z. Now that was cute, but it's nothing compared to the application we're gonna talk about in this video. In this video, we're gonna talk about the Haribo theorem. Even its name is cool already. Actually, when I was doing math in Moscow, my Russian instructor called this theorem by a really weird name. He called it the hedgehog, let's say hedgehog bleep theorem. I asked him why, and he said, well, it's because when two hedgehog bleep bleep, that looks like a Haribo. It was so weird. Until this day, I still don't know whether or not it's just him, or all Russian people call this theorem by this name. But I digress. Let us state what the theorem is. First, intuitively, what this theorem says is that a ball of even dimension cannot be combed. When you comb it so that all the hair lie flat against the ball, then at the end of the day, some hair is gonna stick out. Mathematically, what does this mean? Well, a ball of even dimension is just S2k, and the hairs on a perfectly combed ball is just a vector field. Because what does it mean for a piece of hair to lay flat against the ball? That just means that it lies in the tangent space to the ball. A choice of a tangent vector at each point of the sphere is just a vector field on the sphere. Thus, the mathematical way to say that the Haribo cannot be combed is that an even sphere does not have a continuous nowhere vanishing vector field. Or equivalently, if Sn has a continuous nowhere vanishing vector field, then n must be odd. Actually, this is an if and only if. This is the content of the Haribo theorem. Now let us try to prove this. Let us start with proving sufficiency. So suppose that n is odd. Let's construct a nowhere vanishing continuous vector field on Sn. For intuition, let's start with the case of S1. If we think of S1 as the unit circle on the plane, then in this case there is the usual nowhere vanishing vector field given by minus y, x. Now, for a general sphere Sn of odd dimension n equals to 2k plus 1, we can imitate this approach and assign to every point P with this coordinate the following tangent vector. As in the case of S1, this is gonna be a nowhere vanishing vector field on this odd sphere. So that wraps up the proof of sufficiency. Now let's prove necessity. Suppose that Sn has a continuous nowhere vanishing vector field V. We want to show that n must be odd. Our plan is as follows. Observe that it suffices to construct a homotopy between the identity map and the antipodal map. Why is that? Well, because the degree of the identity is 1, whereas the degree of the antipodal map is minus 1 to the n plus 1. So, if the identity map is homotopic to the antipodal map, then n must be odd. So this is what we want to show. Now, let us construct a homotopy between the identity and the antipodal map. It will be given by this formula as t ranges from 0 to pi. Now observe that this formula is well defined because this is never 0. That is how we use this hypothesis. Now, without loss of generality, just for convenience, let us just assume that V is a unit vector field so that we can rewrite this term as simply Vp. Now observe that f0p is p and f pi of p is minus p. So this indeed gives a homotopy from the identity map to the antipodal map. Thus, this concludes the proof. However, we want to give a bit of geometric intuition behind this formula. Where does this come from? Well, recall that we have assumed that V is of norm 1. Now, if I denote this vector from the origin to P also by P, then Vp must be perpendicular to P. The tangent space to the unit sphere is always orthogonal to the radius. You can see that by differentiating the equation cutting out the sphere. Now, if we look at the plane through the center and parallel to these two vectors P and VP, then we shall see that on that plane, P and VP gives an orthonormal basis. Our homotopy then goes around this circle, the unit circle center at the origin, lying in this plane. It starts from P and ends at the antipodal point of P. Thus, this indeed gives a homotopy between the identity and the antipodal map. And as mentioned, by comparing degree, we see that then the sphere must be of odd dimension. So the hairy sphere cannot be comb. However, you can comb a torus if that's the kind of thing you're into.